In this video, we are going to look at maximum and minimum values of functions. Some of the easy to understand applications would be thinking about a business that has, say, a profit function and wanting to know at what value of input, say, the price of a product we're selling, when that would yield a maximum profit versus when we would be at a minimum profit. Here is some background information with definitions that we'll be using as we look at specific examples. So suppose that we have a function with a defined domain. The function has an absolute maximum or an absolute minimum if it acts as the highest or the lowest point for every x value in the domain. So it's easy to see when we talk about, say, a parabola like x squared here, where the vertex is the lowest point for any of the other x values. And so we would call that an absolute minimum. In this first picture here, there is no point that has an absolute maximum because we know that the function is continuing up to positive infinity in both directions, and so it doesn't have a highest value anywhere. But if we were to restrict the domain, let's say in the second picture, we're going just between x is equal to 0 and x is equal to 2, well, now we can say that there is a maximum value that occurs at this endpoint when x is equal to 2. The minimum still stays at the vertex there. Looking at the third example, letter C, in this case, we're restricting the domain to be everything right up to but not including 0, and then going up to x equals 2. So similar to the last example, we still have an absolute maximum on that restricted interval, but we don't have a minimum per se, because every x value that we choose that's really, really close to 0, let's say we choose x is equal to 0.1, well, we could just pick another value that's even closer to 0, right? And continuing on and on, we can never get a value that's going to be the very, very minimum because we have this open interval there. And then similarly for this fourth example, if I have a complete open interval going between 0 and 2, there's not going to be an absolute maximum or minimum anywhere in that interval. So how we restrict the domain or the interval that we're looking at is going to determine whether or not we can find what are called absolute extrema. Absolute extrema. This is the plural for extreme points, meaning an absolute max and an absolute min. We often use this term when we're trying to just put maximum and minimum together. So this slide is looking at the extreme value theorem, and we have to start with a continuous function on a closed interval. And the theorem is saying that the function will have both an absolute maximum and also an absolute minimum value somewhere in that closed interval, specifically thinking that we have these square brackets on the endpoints, because as we saw in the last examples, the open interval will not lead to a maximum or a minimum. What's written here down below is just sort of the more mathematical version of what's written above. We have two specific numbers, let's call them x sub 1 and x sub 2, and they're in this interval a to b. And if something is an absolute minimum, we're going to use the letter small m. And for absolute max, we're going to use capital M. And we're just saying that every other x value that we choose in the interval a to b, when we plug it into the function, we're going to be somewhere in between that minimum value lowercase m and that maximum value uppercase M. On the right here, we have a couple of different examples. The interval, again, is going between A and B in all of these cases. we can see in this first example that our absolute maximum is occurring here, and our absolute minimum is occurring down here. This is an example where the max and mins fall somewhere between the points A and B, as opposed to this second example where the absolute max and absolute min happen to occur at the endpoints. And then the two examples below are combinations of that, where maybe we've got one of the points being a maximum at an endpoint and somewhere in the interior, or vice versa. So we can have all different possibilities. Now, it's important that we have continuity in the extreme values theorem, because in this example here, we have a function which is completely defined between 0 and 1 for all of the values between and including 0 up to 1. We're taking just the line y equals x, so we've got this part of the graph. And then specifically when we're at x equals 1, then we're having the function value be 0. So we know that there's a minimum, and it shows up in two places, right? It's showing up here at x equals 0 and also at x equals 1. That's the lowest y value on the graph. But because we don't have continuity, we have this jump discontinuity, right? We can't say that there's a maximum value. We can get really, really close, but every time we find a y value, we can just plug in another x value that's closer and closer to 1, and then have a new max value. This is a slide that shows a slightly different definition from the absolute max and min. So absolute is going to be that maximum point is going to be the highest point for any other x value in the interval that we're selecting, or for the function overall, if that's appropriate. But a local max and a local min is going to act like a maximum just in the area around it. So this looks like a maximum point, but we know it's not the maximum point overall because there's points over here that are higher. Similarly, this point here is what we call a local minimum. It looks like the lowest point in the neighborhood around it, but we know that there are other points down here that are lower than that value. And when I say lower, I mean the y value. So a local max and a local min act like a maximum and a minimum, just we say within the neighborhood around them, and some interval. We can define that as we want, just a little bit to the left, a little bit to the right, on either side of the point in question. Now, the reason that we're defining local max and local min is because we're going to use this for an important theorem that we'll be using for later problems. The first derivative theorem for local extreme values, local max and local mins. The theorem says that if we have a local maximum or a local minimum, looking at this picture, we're saying, okay, there's a local maximum here, but it could be that the function goes like this, and maybe somewhere else there's actually an absolute maximum. But just in this little region here, we have a maximum point. Then the derivative at that point is equal to 0. And we give it a special name. We call it a critical point. Now, what this picture is showing you is, and it's kind of leading to the proof that we'll do, is that if I look at secant lines, here's a secant line here, picking some point on the graph, connecting it with that local, or the point we're calling a local max, versus, let's say, the next secant point, the next secant line, sorry, here, and so on. Everything to the left of this point has secant lines with slopes that are positive. On the other side, over here on the right, all of the secant lines have slopes which are negative. So, sort of looking at this as a graph proof, We've got slopes on the left that are positive, slopes on the right that are negative. So somewhere in the middle, if I go from positive to negative, I've got to go through 0 at some point. And so we'll show that the slope of the tangent line there is in fact going to be 0. Once we know what the critical points are, we can use that to find the absolute extreme points, absolute max, absolute min. And we'll do that by finding all the critical points using the derivative. And then we'll take those critical points and plug them into the original function because we want to know what the y value is. And then the largest would be the max and the smallest would be the min. I'm going to first show you the proof of this theorem, and then we'll do a couple examples going through the steps of 1, 2, and 3. So I just made a little room here to do the proof. We want to show that at a local max or min point that, and let's say at the point C, we want to show that the derivative there is equal to 0. So kind of along the lines of what I was just showing you in the picture, what we're going to do is we're going to show that the derivative at C cannot be positive, and then we'll also show that it can't be negative, and so then overall it's got to be equal to 0. And I'm going to do the proof once for local maximum because the proof is almost the same for local minimum. All right, so let's first suppose that our function f has a local maximum point at x equals c, some value c. So based on the definition that we just saw, that means that f of x, all x's around there are going to be less than or equal to f of c, right? So picture-wise, we've got our graph. C is here. This is the point C, f of c. And if we take a neighborhood around this point, x values around here, all of those points, any other f of x that I plug in, let's say here, f of x, is going to be lower than that f of c, right? So for all x values near c, moving the f of c over to the left-hand side, we can say f of x minus f of c is less than or equal to 0. So the point C is in the domain of f. So we know that the derivative is defined, kind of going back to the original way that we defined the derivative using limits. We're going to define it using the limit as x approaches c, f of x minus f of c over x minus c. Because this, and again, this is going back to the way that we originally defined the limit, we started by saying the limit can only exist if both the left and the right-hand limits exist. So we're kind of going backwards here. We're saying, okay, we know the derivative exists. That means that the limit exists. That means that both the left-hand and the right-hand limit exists. So let's look at the right-hand limit, which would be, oops, looking at the limit as x approaches c from the positive side. And then also the left-hand limit, It's going to be identical to this, so I'll just copy this. And then the only difference is going to be that instead of coming from the positive side, it's going to come from the negative side, right? So both of these exist. Okay. Now, here's the part where it gets a little interesting. Up here, we said that this quantity is a negative number. That's showing up here, and that's showing up here. So we know that this, I'll make it purple, this is going to be a negative number up here. This is going to be a negative number, something less than or equal to 0. Right? All right, what happens for the denominators? Get rid of this, oops, this highlighting. Let's look at the denominators now. For the one on top, looking at our picture up here, we're saying that x is approaching c from the positive side. So we're talking about an x value being over here. So x minus c is going to be a positive number. Looking at the one down below, we're approaching from the left-hand side. So x is going to be here, approaching this direction. So x minus c is going to be a negative number. So putting this all together, I think that this quantity here is going to be less than or equal to 0. I've got a negative number divided by a positive number. I believe, I'm going to write it this way. I'm going to say that this whole thing here is less than or equal to 0. And then the one down below, I've got a positive number divided by, or sorry, a negative number divided by a negative number. This is going to be greater than or equal to 0. So I've got the exact same limit sandwiched in between something that's less than or equal to 0, greater than or equal to 0. Putting those two together, we've got to conclude that, in fact, the limit, and in this case, the derivative at that point C, has to be equal to 0, which is what we wanted to show. So we showed this for a local maximum. If we wanted to show it for a local minimum, we would do the exact same thing. The only difference would be that up here, when we said that all f of x values were less than or equal to f of c, we would have switched that, and it would have been greater than or equal to. And so then this would have changed to greater than or equal to 0. Same thing would happen down here with the fractions of the limits. We would have positive over negative versus negative over negative, and we would get this these two limits sandwiched in between 0. But either way, we've shown that the derivative at any critical point is going to equal 0, which is really useful for finding absolute max and min points. All right, so let's do a couple of examples. So we have a function. You can see the graph here, so we can see the answers that we're working towards. But we have a function and we want to find the extreme values, and we have a particular interval between 0 and e squared. We know that we're going to test the endpoints, but we also have to test any critical values, which is where the derivative is equal to 0. So the first thing we'll do is find the derivative of this function. We need to use the product rule here. Let's call this g and let's call this h. So we'll take the first function times the derivative of the second, which is going to be, the derivative of 2 is going to be 0, and then the derivative of natural log of x is 1 over x. So this is the derivative of the second function, plus the second function times the derivative of the first, which is 10. Okay, let's simplify this. So it looks like I've got, that's going to be a negative 10 for the first part. And then I'll have a plus 20 minus 10 natural log of x. So it looks like I've got 10 minus 10 log of x. Okay. The next thing to do is we want to determine when does the derivative equal 0, because that'll give us the critical numbers. So when does f prime of x equal 0? So 10 equals negative, oops, forgot the log there. Negative 10 natural log of x, that would be positive. Divide both sides by 10. So I'm saying 1 is equal to natural log of x. That's going to happen when x is equal to e. Okay. So we're saying that x equal to e is our critical number. So what we're going to do now is we're going to take that critical number and the endpoints and we're going to plug them into the original function to see what gives us the max and the min output values. So again, the original function was 10x times, oops, 2 minus natural log of x. Just double check. Yeah. So we're going to test the critical number x equals e. We're also going to test the endpoints. X equals 1 and x equals e squared. We're plugging them into the original. So let's see, f of 0 is why am I testing 0? Pause. When I do crazy things, you got to stop me. Our critical number was at E. I had random things showing up on my screen that got me a little kerfluffled there. All right, we're good. We're going to test x equals E. So we're plugging this into the original equation. So 10 times E, 2 minus natural log of E. 10E, this will be 2 minus 1. So this is going to be just 10E. All right, plugging 1 into the equation, f of 1 will have 10 times 2 minus the natural log of 1, which is 10 times 2 minus 0. So this is 20. And then plugging e squared in, we'll get 10 times e squared times 2 minus natural log of e squared. 10e squared. And then this will be 2 minus 2. So we get 0 for this one. So looking at our 3 output values, it looks like 10 times e is going to be higher than 20. It's about 27, right? So this will be our max point here, and this will be our min point here. So our max was at E 10e, and our min was at e squared comma 0. Looking back up at our graph here, here was our max, here was our min. All right, let's do another example. This is a different example. Again, you can see the graph here, which can help you. But the math behind this would be to find the derivative first. So f prime of x will be, we'll bring the 2/3 down and then drop the power down by 1. Rewriting this, I'll get 2 over 3 times the cube root of x. So when does the derivative here equal 0? Well, it looks like never, right? But it is undefined at x equals 0. So a critical number shows up in two possible places. One, when the derivative is equal to 0, or 2, if the derivative is undefined. So our critical number in this case is going to be x equals 0. All right, so we're going to test the critical number x equals 0, and then we're also going to test the endpoints, which were -2 and also 3. All right, so plugging this in, f of 0 equals 0 to the 2/3 power, which is just 0. That one was easy. F of -2, -2 to the 2/3 power. What I'm going to do is I'm going to square this first. That'll give me a 4, and then I'll take the cube root of that. So this is going to be the cube root of 4. And then similarly down here, I'll square the 3, which will give me 9, and then take the cube root of that. So looking at our three values, obviously this is going to be our min at 0, 0. And this is going to be our max at 3 cube root of 9. So looking back at our graph here, yeah, we had the absolute minimum here, and then we have our absolute maximum here. This is saying that it's a local maximum because in the neighborhood around it, it does act like the highest point, but it's not the highest point for the graph overall, because we know that over here when x is equal to 3, the value is actually higher. All right, thank you for watching this video. We'll do more examples like this in class. Have a good day.